Now that we've defined the CTL syntax, we are moving towards defining the semantics. For this, let's recall the notion of label transition system, which was of course central for the LTL semantics as well. Recall that a label transition system, LTS for short, is a triple M consisting of a finite set S of states, a relation arrow between the states, and a labeling function L that labels each state with a set of atoms, thought of as the atoms that are true at that state. And we assume that each state has at least one outward transition, that is, we can never get stuck while transiting between the states of the system. Also, recall that a path in an LTS is an infinite sequence of states such that any two consecutive states in the sequence are connected by a transition, and that we write paths as M for the set of all paths in M starting in the state S. Now, here's an important difference between the way LTL semantics was defined on LTSs and the way we'll define the CTL semantics on LTSs. Remember that for LTL, we first defined what it means for an individual path to satisfy a formula. And only after that, we define what it means for an entire LTS to satisfy a formula. Namely, we said that the LTS in a state S0 satisfies an LTL formula, provided all its paths starting from S0 satisfy that formula. In other words, for LTL formulas, LTS satisfaction was reduced to individual path satisfaction. This means that the branching structure of an LTS, that is, the realm of transition possibilities in each state, was not contemplated directly in LTL semantics, but only indirectly via all possible paths. One can say that in LTL, all the possible futures of the world are packaged in the form of infinite paths. So there's no branching between different futures that can be explicitly considered at given states. By contrast, in the case of CTL, we'll define the semantics of formulas by engaging directly with the branching structure, that is, with the realm of possible transitions from given states. Namely, we will define the semantics of CTL formulas directly on LTSs. For explaining the CTL semantics, it's best to think in terms of the unwinding tree of an LTS, also known as its computation tree, which, by the way, gives the name of the logic. CTL stands for computation tree logic. Recall that the unwinding tree of an LTS, starting from a given state, say S0, is the infinite tree that has S0 as its root, and at each level, it applies the transitions of the LTS. It never looks back, but rather makes copies of the LTS states when moving to a new level. In the example shown here, we start with S0 as the root, and we follow the LTS system shown on the left, and see that, for example, S0 has two transitions, one to S1 and one to S2. So this is what happens in the tree. We have two transitions from the root S0, one to a state S labeled S to a state that corresponds to S1, and one to a state that corresponds to S2. Then we see in the LTS on the left that S1 can transit to S0 and S2, and S2 can only transit to itself. And again, this is reflected in the tree. S1 transits to S0 and S2, and S2 to S2, and so on. Again, the tree never looks back, but only forth. And the important thing is that the unwinding tree is a faithful representation of the LTS in that it has the same path starting in S0 as the LTS. In what follows, We'll use the unwinding tree representation of an LTS in the informal examples and for explaining intuitions, although the formal definition of the semantics will refer to the original LTS. The unwinding tree of an LTS will be just a visual aid.